Welcome to Study Loop.
Okay, I'm just going to do a forward direction synthesis here. And what I would point out is that nothing changes between the starting material and the final product, other than that, where previously we had a carbonyl, right? We end up with this. Okay, so anything that happens over here doesn't matter. Nothing on this side will be reactive to any of the reagents we use or make any sort of difference whatsoever. Okay. Yeah. Then the other thing that I'll notice is that, well, we're shown this reagent that we can use. Okay. Notice that it contains 1, 2, 3, 4 carbons, and that all we've added to our molecule is 1, 2, 3, 4 carbons, right? So this is our source of carbon. Okay. So our first order of business is attaching this at this carbon, right? Well, to me, that looks like a Grignard reaction, right? That we took our this reagent here and reacted it with magnesium and diethyl ether, okay, to form what is essentially a nucleophilic source of carbon. Right, this is one way that we can conceptualize a Grignard reagent. And that if we react this with our substrate, it will only add to one place, and it will give us the alkoxide. So we'll finish up with a aqueous workup, acidic aqueous workup, to give us the alcohol. Right, we'll get this, and we'll get that. Right, we've added our 4 carbons. Now the next order of business is, how do we get this oxygen to attack that carbon? Okay, and then we'll at some point have to get another molecule of hydroxide to attack this carbon. Well, we can kind of accomplish both of those in one step, right? If we react this with Br2, for example, we will be adding bromine across that double bond, right? Like so. Now, technically, these will be anti to each other, but since this is not a stereocenter, it doesn't really matter. Okay, now next, recall we want to add a hydroxide to one of these. How can we selectively add a hydroxide to one and not the other? Well, one of these bromines is on a primary carbon, the other is on a secondary carbon. If we react this with sodium hydroxide, which should displace one of the bromines via an SN2 reaction, it's going to selectively add to the primary carbon, right? Because SN2 reactions prefer to happen on primary substrates, right? So then we should expect that the product of this reaction will be right, and we'll still have our bromine here. And at this point, we could deprotonate this to basically we're going to influence an intermolecular SN2 now that all we've got left is the secondary hydrogen. You may want to, before doing this, protect this alcohol so that we don't simply deprotonate it, but it shouldn't really make much of a difference. But we could do that, right? We could say react this with like a silyl ether or something first, right? Like TMS followed by TBAF to install a silyl ether and then remove it later, just so we don't get deprotonation there. But I'm fairly certain that it's not necessary because this is going to be more attracted to this electrophilic carbon than this proton. Nevertheless, that's something you may want to consider. Okay, at this point, if we react with sodium hydride, right, we'll generate the hydroxide, or sorry, the alkoxide again. And that alkoxide, right, once we've abstracted that proton, we'll perform another substitution reaction, and that will give us our final product.